we'll be looking at the same formula here, right? We'll be looking at the same formula here, except for now my omega is a whole domain, actually a real domain. And the gradients of these basis functions are gradients inside these triangles. But again, these gradients are going to be constants within each triangle, right? So again, I'm looking at the integration of the product of two constants. All right. Just like in the 1D case, the Kij is going to be 0 if I and j does not share an interval. In this case, again, if I is here and j is here and they don't share a triangle, they don't share any, this is where j would only be non-zero if I and j are sharing some triangle at least. Okay. And there are two cases again. One case is when I and j are the same. So they're going to be sharing as many triangles as there are around this point. Or when I and j are just one edge apart, in which case they are sharing how many triangles? Two, right? Okay, and so we won't count on the fact that they are only sharing two triangles, because when we go to 3D, I mean, you have no idea how many tetrahedrals each pair are sharing. But like, so we'll be filling the matrix incrementally over each triangle instead of trying to build it like at once, like what we did last time. So we are going to add small increments to the matrix for each triangle incrementally. Okay, which means we'll be looking at, we are going to be splitting this integral. Oh, let me actually go to the we'll be splitting the integration of grad phi I, grad phi j into an integration over ek. So let's say k is the element index, grad phi I, grad phi j dx. Okay. So if this is summation over k, so if this is the matrix Kij, this is the summation over small k of Kij k. All right. So Kij k is the contribution of element k or triangle k into the entire matrix. Okay. Okay, so let's start looking at what these integrals are. So we know, like, this is a constant within element k. So let's calculate these constants and do this integration. Okay, we want to calculate for the element. This is element k. It has 1, 2, 3 nodes, and also 1, 2, 3 basis functions that are going to be non-zero within that interval. So let's calculate what the gradients are for each of the basis functions. For the basis function that is 1 here and 0 elsewhere, we can calculate the gradient by this. So delta phi, so the x component, y component of this, okay, times a matrix times the matrix of x, let me see. Okay, so what do we want? Let's see this, x1 minus x2. I need a matrix. x1 minus x2 y1 minus y2, this should be equal to what? So, I mean, the grade, we got a linear function here. So the gradient of that linear function dot product with the delta x that goes from 2 to 1 should be equal to should be equal to 1 minus 0, should be the difference between the value of the function here and here, right? So it should be 1 minus 0, or 1 minus 0. If I do the same thing here, x1 minus x3 and y1 minus y3, it should be the value of here minus the value of here, which is again 1 minus 0. So basically, I can compute the gradient of the basis function by inverting a 2 by 2 matrix. All right. Any questions here? And similarly, let me say phi1 because it corresponds to node 1. Similarly, the gradient of the basis function corresponding to the other grid points can be computed exactly the same way. Okay. Do we have a question here? Because I'm going to put that into the code. Oh, all right. Oh, we need to generate. Let me clear. We need to generate a mesh first. So let's use the ODE tool, PDE toolbox. Let's do this mesh and export. Okay. So we have EPT here, and P is the nodal positions, T is the triangles. Actually, T the first three rows of T are the index in the P array that corresponds to which of the 3 points are forming all of these triangles. The last row is always 1 because we only have one domain. If you are making multiple domains, these correspond to which domain the triangle lies in. Okay, so that's what we have, and we want to, for each t, compute the gradient of each of these functions. Gradient. So first of all, we want to make a gradient array that is equal to zeros is equal to, first of all, the number of, let's do this, the number of triangles, 238. Okay, and we will have 3 different basis functions within each triangle, right? So I'll put 3 here, and it's also going to be 2-dimensional because I have the gradient has 2 numbers, x and y. Okay, so that is going to be my gradient. I'm going to, for k goes from 1 to the number of triangles. Okay, so I'll have P1. I have P1 is equal to P column. The first index is x and y, and the second index is gonna be P of 1k. Okay, and I'll have P2 equal to this, and the P3 equal to this. So I'm looking at the coordinates of these three points. Okay. And when I'm computing the gradient, I'm going to say gradient of K1 column is equal to, I'm going to be trying to invert this matrix here, and 1 and 1. So I'm going to have a matrix backslash 1 and 1, right? And the matrix should be what? Actually, let me compute this matrix first. Without doing this. So let's say I call the matrix dx. Okay, the dx is going to be P1 minus P2 and P1 minus P3. So I think P1 and P1, P2, P3 are all column vectors, so I need to also transpose them. So P1 minus P2 transpose, P1 minus P3 transpose. Okay, that's going to be this matrix over here, right? And then my gradient of K and the 1 and the column is going to be dx backslash 1, 1. Does that work, or do I need to transpose? So let's try it anyway. Okay, so for the other one, when I'm looking at point 2, it needs to be 2 minus 1 and 2 minus 3, right? Because now P2 it has value 1 and all the others has 0. And 2 here. And the last one is P3 has value 1 or else has value 0. So I get 3 here. Hopefully it'll work. Looks like it's working. So the value G here, it no longer can print it. So, okay. Anyway, so I get a value of G that has the number of elements times 3, which is the number of nodes, and times 2, which is x and y directions. In 3D, this guy would be the number of elements times 4, because I have 4 nodes, times 3, which is 3 dimensions. All right. Okay. So now I computed the gradients. So my matrix K is going to be okay. So let's build the matrix K first, including the boundary nodes, and then let's remove the boundary nodes from the matrix. Okay, because that's easier, because right now I don't have a list of what are the boundary nodes, what is not. Okay, so let's say 0s 238. Okay, so where is my K? Yes, okay. So for small k goes from 1 to 238. I'm going to incrementally add the entries. So first of all, I want to know what the entries are. So I want I1, I2, I3. These are the entries would equal to the value of T at 1, 2, 3, and K, right? Maybe I should do column. Okay. What? So actually what I did was more correct. Okay, so these are the node index correspond to the 3 nodes in that element. Okay, so my K I1 is equal to K I1 plus the contribution from that element, and that contribution would be the size of the element, which I didn't calculate. So let me end here. Okay, number of insufficient number of outputs from right hand side equal to sign. Okay, maybe I need to transpose on the right hand side, but let's compute the area first. Yes, question? K would be the stiffness matrix. Yes. Good point. So K shouldn't be the size of the number of elements. It should be the number of nodes. Okay,